So I would like to thank the organizers for giving me this opportunity to talk here. It's really an honor to be here, and it's such a marvelous conference. I'm waiting for the recordings. Yeah, so today I'll talk about certain kinds of quantization called Berezin-type and Fedosov-type quantizations on arbitrary smooth manifolds. So these are quantizations which are both in the family of deformation quantizations. So I will, maybe I'll talk about that first, but it's way down. Sorry, my slides are not very organized, but so I'll start with Fedosov quantization. So let me tell my philosophy a little bit. So this is a new venture I am having. So, usually for geometric quantization and all kinds of quantization, canonical quantization, you need conjugate variables, you need a symplectic form. And so, but in real life, where is the symplectic form, right? You are in R3. And so even odd dimensional manifolds, you would like to see it quantized in some sense. So what we do is embed it in symplectic manifold, or CPN or CN, or any other symplectic manifold which has certain structures, and induce the quantization from there. And so there is a lot of dependence on the embedding, and it's just just started. So I will just say whatever little I can about this. So this was a work with, unfortunately, because of the switch, Satyan is not here, but it's a work in progress with Satyan Patil for his MSc thesis project. And he's from IISER Pune. He's very smart. So he keeps me on my toes. So the problem Fedosov answers for symplectic manifolds is as follows. I've quoted from his paper. The problem is to define an associative multiplicative operator, which is called the star operator, depending on a parameter h, Planck's constant, of two functions, so that the space C infinity M with usual linear operators and star product would be a formal deformation of commutative algebra of functions with a Paycha bracket. So more exactly, it means the following. So Z is a linear space with elements of this form, where AX, AKX are in C infinity M. For any two such objects, let an associative product operation be defined as C summation CKX H to the K, defined along with the following properties. CK are polynomials in AK and BK and their derivatives. C0x is the first coefficient, is just product of the two, and the commutator of the star product up to H cross minus I H cross is just the Paycha bracket. The Paycha bracket induced by the symplectic form. And there are other higher order terms, but I think standard theory of quantization, this is a must. Dirac's first, I think from Dirac's time, he just laid it as a postulate that commutator of operators should be proportional to the Paycha bracket up to first order. This algebra is called Z is called the algebra of quantum observables. Property 1 says locality of the star product. Property 2 means Z is a deformation of the commutative algebra C infinity of functions. And property 3 is called the correspondence principle. So Fedosov constructs this star product for a symplectic manifold, which has a non-degenerate Paycha structure induced by the symplectic form. Our main aim is to define this on a smooth manifold embedded in X, which has a possibly degenerate Paycha structure locally induced from the 1 on X. So how do we induce the Paycha structure? X comma omega is a symplectic manifold of real dimension 2n. Then there is a top dimensional cell, right? There's a cell decomposition, and there's a top dimensional cell which is homeomorphic to R2n. and x minus u is of dimension lower than 2n. So I embed it, embed the manifold into this, into R2n. Any embedding actually would do, but I'm saying R2n because then we can embed it by the Whitney embedding. Whitney embedding, sorry, this is n and this is R2n. So just to give an example, but actually you can use any embedding. There could be other embeddings too, and what follows holds for all of them. So locally, using inverse function theorem, you can think of the epsilon locally as, so epsilon m, so let me just say it on the board. So here is m, here is x, and here is m sitting there. So there is a neighborhood V such that V intersection epsilon m. So this is, sorry, this is my m, this is epsilon m. There is a neighborhood in which this embedding always looks like x1 till xn 2n such that, so this is d-dimensional. So you can set the other indices to be 0. So this is by inverse function theorem you can do because it's a embedding. And so we will use this again and again. But one thing to note is what we will do actually doesn't matter which coordinate you choose. I'm just picking this coordinate because it's very easy to describe the quantization.
Sorry.
Yes.
What did you mean? So you have M of
Yes.
dimension D.
Yeah.
You're taking a map. What kind of map is this?
It's an embedding.
It's an embedding. Okay.
Yeah. Embedding. And
into what space?
Into an X, which is a symplectic dimension, symplectic manifold.
Then
and then I'm saying, so x1, x2, xn are the coordinates in Vn, right? V is the neighborhood in the bigger space. What I can do is I can take x1 till xn, xd to be non-zero. There is a neighborhood in which the embedding looks like this. So these are the floating variables on this neighborhood, and the other neighborhoods is 0. So you can slice it. This can be done locally because it's an embedding. So we will use this coordinate because our thing is very easy to describe in this, but it's coordinate independent. Okay. So so first of all, local Poisson structure. So first of all, you know that there is a Poisson structure induced by the symplectic form. So it is actually this thing, summation ij goes to 2n omega ij f1. So let me just write it. So summation omega ij del f1 del xi del f2 del xj. This is the inverse matrix for the symplectic form matrix. So this is I goes from I and j going from 1 to 2n. And I want to somehow restrict this to the lower dimensional manifold. It could be even odd dimensional. So what we do is we just restrict it to epsilon m. This is epsilon m. This object is epsilon m. Yeah. I restrict it to epsilon m, leave out all the derivatives which do not involve leave out all the derivatives leave out all the del xj's which are from xd plus 1 till x2n. I leave out those and then pull it back on m. So that's how we define it. And one can show that it's not non-degenerate anymore, but you can show that it satisfies Jacobi identity. Okay, so now small omega is defined on the symplectic manifold only. We just restrict it. It could be omega ij was a matrix which depended on the x1 till x2n. I just restrict it. I just set those to be 0. It need not be invertible anymore. There is no such thing anymore. Yeah. So It's not, that's why I'm saying it's not a non-degenerate symplectic form. It's not a non-degenerate Poisson bracket. It could be degenerate, it could be zero also. So D can be any dimension.
Sorry.
Yeah, x2n. Sorry, this was the coordinate on the bigger one, x2n. And then of that, I am setting, yeah. Okay. So now review of star product, how Fedosov does it on a symplectic manifold. It's a little complicated, but I'll try to go through it. So the x and the, so I look at the tangent bundle, x1 till x2n, y1 till y2n. And on our special manifold, it looks like x1 till xd, 0, 0, 0, y1 till yd, 0, 0, 0. Now there is this section of Weil algebras on X which look like these. Okay, so these are just functions, and then I have the y1 till yj. And let us consider two elements AB of the Weil algebra in the fiber. So then there is a circle you can define. This is somewhat like the Morel-Weil product. You may be recognizing this. So this is like A circle, B is this. And this can be defined on epsilon m by setting all the del del yi's to be 0 if d I equals to 1 to d plus 1. All those d plus 1 to 2n, I'm sorry, this should be 2n. D plus 1 to 2n, we just, and then do not, so I first restrict it to epsilon m, and then I remove all the derivatives which do not involve these. And then to define on m, we push forward the contravariant. So from m to epsilon m, so from m to epsilon m, epsilon is a diffeomorphism. So epsilon and epsilon, so epsilon m to epsilon m, and epsilon m to, so these are, I'm assuming these are diffeomorphisms. Okay. And then what I do is I push forward the contravariant tensors by epsilon star inverse and pull back the covariant tensors by epsilon star. So this is how I define it on the M. Okay, so this is how I define it on M. And now this is not enough. You have to also introduce differential forms. So these are just Weil algebra tensor with some differential forms of dimension P. And then again we do the same. We just restrict it to epsilon m and remove all the ones which do not contain these and all the variables which do not contain this, and then pull it back to m. So this is how we define the A tilde xyh on m. So now Zx be the algebra of quantum observables for x. How did Fedosov define the star product? Well, that was a long story, but what he does is first constructs a flat connection on the Weil algebra, Weil bundle. And then for each C0, there is a unique lift, sigma inverse C0 to this flat connections. We need flat connections for this uniqueness, special uniqueness property. So sigma C is sigma. So this is the symbol of C. And how is the formula? The formula is given by C equals to C0, del I C0, yi, and so on, so on. And there is the curvature term, which is the curvature term which comes from this flat connection. So this is how you go back from C to C0 and C0 to C. So back and forth. And the Fedosov star product is just you take C0, invert it, get to C, do that Moel type of product, and then take the symbol again. That's how we define the Fedosov star product. And it is associative, all the correspondence principle holds, all the properties are very nice. So now our our job is now very simple. We just do the same thing on Zm, but we restrict everything for all the quantities, all the objects. We first restrict it to epsilon m. We remove all the derivatives which do not involve the epsilon m, and then do the star product as follows. Star product as follows. Yeah, so A0 tilde and B0 tilde are the sections of the, so this phi operator I have just means I first restrict that flat while the flat sections to epsilon m, and then I take phi, which is like removing all the indices which involve this d plus 1 to 2n, and also phi also denotes the push forward of the covariant tensors by epsilon star and pull back by epsilon star inverse of the contravariate tensors. So in that case, I get I get these objects on M, and let A0 tilde and B0 tilde be their symbols, and our job is very easy. A0 tilde star, B0 tilde star B0 tilde is just epsilon star A0 star with epsilon star B0, which is just epsilon star A0 F B0. And how are these two related? Well, where those forms do not occur. These ones do not occur. Yeah, the phi was the map. Where did I write it? Phi was the map. Sorry, let me just say in words. Phi is the map. What I'm doing is, first I'm restricting everything to epsilon m, and then this operation, sorry, this operation, this kind of operation, the sections of the tangent space I'm doing with pulling back by epsilon star inverse, and the I mean pushing back actually to m, and all the functions I do epsilon star, and the forms also epsilon star, and then I also remove all the derivatives and these things which do not come in this. On M itself. Yes, on M itself. So on M itself, I have defined the, yes? Any questions? Yeah, sorry, yeah. So that's why A0 tilde, sorry.
Phi, right?
Yeah, so phi is that entire map. I had defined it somewhere, but I lost it. Phi is that entire map process of first restricting to epsilon m, then removing all the coordinates which are not relevant for us, and then epsilon star and epsilon star inverse. This whole thing I'm calling it phi. So, so that is A tilde, B tilde is phi of this. So yeah, here I have written some caricature of it. Phi is the push forward and pull back map. And we omit from Wx the indices which involve I equals to d plus 1 to 2n. So this is the star product, and it is a little bit huff and puff, but we can actually show that it also satisfies the correspondence principle. And associativity also follows from this thing. So the star product we have defined this way is associative, and also the correspondence principle holds. So this is, so this was Fedosov. Do we have any questions? Any questions? Yes. Given M.
Restrictions on your mapping on the epsilon?
So far I have, except, sometimes the Paycha bracket can just collapse. I don't want that. So as long as the induced Paycha bracket doesn't collapse, I think we are good. I don't know, this is...
But the properties then, they're the same more or less?
Yes, as long as it's an embedding, there's no problem. So there is a lot of choice actually. Yeah, so... Yeah.
You can induce for every embedding the structure.
different structures. Maybe there's
So
a
every
way to
embedding
go.
will be different
Yes,
structure.
yes.
The
Yeah.
other question, of course, is existence of the embedding. So it's not, I mean, I
Yeah,
don't know
embedding exists, for example, the Whitney embedding. If you embed it into 2-dimension more, MD is a compact,
Yes.
supposing it's a compact smooth manifold,
So that is as a manifold embedding.
you embed it into R2N first, and R2N is sitting inside CPN very nicely. CPN, for instance,
Symplectic
or even symplectic manifold, R2N is sitting inside as the biggest cell. So far there's no restriction. Yeah, so that is what I was thinking. And then let's go back to Berezin. Again, Berezin is so how much time do I have? I have some time, right? So, yeah, that will be more than sufficient. So, review of geometric quantization and coherence. Again, here I will embed my manifold into CPN. It's a compact smooth manifold, say. Otherwise, I'll embed it in CN if it is not compact. So now coherent states on CPN. So Berezin considers CPN as a homogeneous scalar manifold and obtains the quantization. But we want to do a local picture because it's our whole construction is local. So let mu1 till mu(n) be homogeneous coordinates on U0, which is homeomorphic to Cn. Biholomorphic to Cn, where U0 is the in homogeneous coordinates is the tau 0 which is not equal to 0. It's the equivalence class of tau 0 to tau n. So now in this setup, CPN is union of I goes from 1 to n ui, right? And the Fubini's 2D form is given by this. I will restrict everything to U0, but that's not the only thing. There could be other possibilities also, but let me just restrict everything to U0. And the Paycha bracket, Fubini's 2D Paycha bracket is given by this. And so this is omega Fsij is the inverse of the omega Fs symplectic form, right? And then you know that the geometric quantization of CPN are hyperplane section bundles H on CPN, sections of those. And they form an orthonormal basis for the space of holomorphic, and the homogeneous polynomials of degree m are the sections, but we want to write it locally. So here these are inhomogeneous coordinates. So H tensor M, so I take tensor product, mth tensor product of the hyperplane bundle, and they can be identified, the sections can be identified with polynomials mu I from I to n of degree at most n. And what's going to be our H cross? H cross is going to be 1 over m. And so far an integer, m is so far an integer, but okay, 1 over m is the H cross parameter. And so everything is going to depend on H cross. So this is the volume. And I just normalize Cm inverse. I have the Keller potential. Cm inverse is a certain number, which I need to normalize things. So the Hilbert space inner product is given by Cm integral U0 F nu bar G nu divided by this dV. And this in this e to the minus m, I can write it as a Keller potential, e to the minus m phi Fs dV. So now I just normalize the polynomials and I write these are orthonormal. I write the basis, orthonormal basis for the Hilbert space as this. And Now, given an orthonormal basis of a Hilbert space, which is a reproducing kernel Hilbert space, which I'll talk about a little later, there is a Ronsley-type coherent state on U0, which is given by this. So phi, this is this mu, and then I multiply it with this evaluated at mu, bar, and summation. So this is my coherent state. And I will write it in short as psi mu. Mu is the parameter running over U0. And this is the, you may be recognizing it as the reproducing kernel. So I will probably do that, but reproducing, so this coherent states has the reproducing kernel property. That means if you take any psi, a section of the Hilbert space, if you take the inner product, you just evaluate psi mu. If you take the inner product with psi mu, you just get psi evaluated at mu. And in particular, this is, I didn't write the form of this. This is actually very nice. 1 plus mu bar dot mu to the power m. So this is the reproducing kernel for CPN. And I have the resolution of identity property. And yeah, so, and over completeness property. So these are the candidates for coherent states. And if you have the coherent states, you can actually talk about the symbols of bounded linear operators, right? So, okay, first, reproducing kernel Hilbert space on a compact smooth manifold. Yes, yes, yes.
At least in the physics context, one knows about coherent states.
Yeah, yeah.
Ones where you minimize the,
Uncertainty. Yeah.
Here, what makes these different?
These are the same. These also will have minimizing uncertainty principle, I think, because you can prove it using reproducing kernel and resolution of identity.
Why are they called Ronsley-type?
Ronsley-type, because it's written in a little different way, using the basis of the Hilbert space. And also, of course, there are the parallel of ones. Parallel, you move it by the group. And for CPN, I think both are the same. Like in SU, I think in SU2, you get the coherent states by moving it around the group, right? With the group action. SU, sorry, I don't know very much. Yes, yes.
As I know, only for the coherent, for the oscillator, harmonic oscillator,
Yes,
we can
yes.
build the coherent states which satisfied three conditions. So it is the related with the group, or minimize the uncertainty relation, or they are the eigenvalues of some ladder operator,
Yes,
the lower ladder operator. But here, when we generalized, one of these conditions should be satisfied. And moreover, it should be resolution of identity satisfied, reproducing kernel exists, the complex parameters.
Yes.
I believe that it is mu.
Yes.
Yes. So it is the generalized version. And of course, it should be related with some algebra, because you have the sum of Q1, Qn is equal Q. So it should be related with SUN algebra, something like that. I am not sure.
Maybe.
This I am not sure. I'm just
But you're right, except it doesn't satisfy the eigenvalue of condition.
Okay.
That is not
Yet,
always
yet,
true.
yes,
Yeah.
yes.
At least even on S2, you can show it's not the eigenvalue.
Okay.
Spins.
Yeah.
CP1 itself, you can show that it's not the eigenvalue. Except that condition, I think all the other conditions satisfy.
Okay. Thank you.
So now the nice thing about this way of defining reproducing kernel is you can pull it back to the subset and define a little slightly different inner product, and it again becomes a reproducing kernel. So that is so okay. First, I'll say a little bit of history. I started this work with my student Kohinoor Ghosh. We did the pullback of the coherent states on a smooth manifold, and so M is embedded inside CPD, and the way you define it is yes. Standard embedding, say for instance, with the inclusion, like U0 is my R2D, U0 could be my R2D, and then what I'm doing is I want to pull back the reproducing kernel on this.
So what is it? I don't the reproducing kernel. So
A reproducing kernel for me is just this kind of a thing which satisfies reproducing kernel property and all these resolution of identity. So the reproducing kernel is this thing. They would, in functional analysis, they will call this psi mu as the reproducing kernel. In the case of CPN, it's 1 plus mu bar dot mu to the power m. This is psi mu mu. This is the reproducing kernel for CPN. When you take tensor product, when it's tensor product of the hyperplane bundle to the power m. Yeah, so this is a standard thing in functional analysis, and so in fact, in functional analysis itself, you get that subsets of CPN will also get a reproducing kernel. So how do we do this? So I pull back the Hilbert space onto this subspace, okay? And before I do pull back on M, I first pull it back on epsilon M, and then, or did I write it chi? Sorry, sometimes I'm writing chi, sometimes epsilon. It's very confusing. In this slide, I've written it as chi. Chi is the embedding. So, and sigma is, here I have written epsilon. I'm extremely sorry. This sigma is chi of M. And first I restrict it to this. And how do I define the norm? Norm I define as CPD norm, but then there are so many extensions, right? So I take the one which is minimizing of inside the Hilbert space. So minimum of S in HM such that norm of S on CPD, S tilde is S composed with I. So, the picture is as follows. I have this CPN. I want to restrict it to restrict the Hilbert space on epsilon M and define a norm on that, but there are many extensions of the sections. I take the one with the minimum norm. And the norm comes from CPD. Okay. This actually, this is a, this thing in one functional analysis book, I found it. It's a book by Raghupati and Nelson, I think. I will come to that later when I do the bibliography. So then I pull it back to there. As before, they are overcomplete, have reproducing kernel property. So, okay. So now I pull it back to M also with the same norm, with the same kind of definition of the norm. And so now if eta is an orthonormal basis from H to M, H to M is the resultant Hilbert space on M, then I can define the Ronsley coherent states as these. Again, same thing, eta ik bar evaluated at P and mu I, okay, where P belongs to M. So this is the Ronsley type of definition. And as before, they are overcomplete, have reproducing kernel property and resolution identity. So again, we induce the Poisson structure as follows. So I'm not going to talk about that. So now the Berezin quantization is very simple. I mean, for us, it's very simple because we have a coherent state already. So how does Berezin quantization work? First, you take a bounded linear operator on the Hilbert space, take the inner product, so the expectation value on psi mu, and construct this operator. So basically expectation value on the coherent states, divide by the norm. These are called symbols of the operator. And on these, he defines the star product. So in CPN, this star product just looks like this. These are just to define, just to be in keeping with his notation, I have kept it as LM mu bar is, I mean, he uses LM mu bar in Berezin's paper. So, so that's why I kept that notation. And this is the formula for the star product. And actually, this is the symbol of A1 hat composed with A2 hat. And the star product satisfies the correspondence principle. This is again a lot of huff and puff, but it satisfies. He showed this in very general case of a Kähler manifold with certain properties. CPN is one of them. So now how do we do it? We actually pull back the operators, bounded linear operators to H2M. And again, there'll be a lot of choices. So we take the one with the least norm. So B hat is chi star A hat. Then this is equal to chi star A1 hat. Then I take A hat to be the least norm operator. And then I have the coherent states already. So I'm going to try to take, yes. Yes.
There are multiple embeddings. For every embedding, you have multiple norms, but you now take the minimum norm.
I'm not minimizing over embeddings. My CPN is.
But can you do that is the question.
Because
then that would give you something that's independent of embedding, right?
Right.
Because of all the non-uniqueness would then go away. I mean, it sounds easier said than done.
Yeah. But I feel we need the non-uniqueness for our problems. Some problems, some epsilon may be more useful than the other. So, so it's not a bad thing to have this independent, dependent on epsilon, I feel. So, so now I have these induced coherent states, and I take expectation value of the A hats on that. So sorry, CPD norm, this should not be M. So these are CPD norms still, but the parameter is chi P and chi Q. So A of this, A of chi P, chi Q bar. So when it goes into CPN, there is Z and Z bar, right? So then it takes on complex character, like chi P and chi Q bar. So, and it's a little bit of work to show that, not very much, that if B1, B2M is the induced Paycha bracket, it will satisfy the correspondence principle. So, yeah, so it follows again because A1, A2 themselves actually, so A1, A2, remember, was B hat was chi star A hat was the least norm. Then that's why this was useful. Sorry, correspondence principle is holding because it held for A1 and A2. So yeah, so actually I've come to the end of my talk. So I'll just go through the introduction. I didn't go for the introduction much, but that could be like a conclusion too. So basically we wish to study systems which do not have symplectic structure or group action, and study if there are semi-classical limit of some quantum system as H cross goes to 0. A Paycha structure is needed, but it is induced from another Paycha manifold where the manifold is embedded, usually a symplectic manifold. And for Berezin, we are using CPN and CN. So Berezin had focused on Kähler manifolds, and that too very special ones. And Fedosov had focused on symplectic manifolds. So we are trying to use their techniques to induce it on smooth manifolds. And as for the literature, Berezin quantization has been generalized to many domains and manifolds. But no one has, I think, so far done it for arbitrary symplectic or arbitrary smooth manifolds, as far as I know. So, so again, we embed it into CPN and pull back coherent states from CPN, and would be other appropriate manifolds too. And Berezin gave a way of defining the star product and the symbols of the linear operators acting on a Hilbert space with a reproducing kernel on a Kähler manifold under certain conditions. There's a parameter which when it goes to 0, star product becomes the usual product, and the commutator of the star product is proportional to the Paycha bracket up to first order, or the correspondence principle. And we also try to see the same for the embedded manifold. And Kohinoor Ghosh, who was my graduate student, so we had done it for totally real submanifolds of CPN, but ours is a little generalization of that because we do not want the totally real submanifold because it can give topological obstructions. And so it can be done in general. And there was another method of doing it by removing a set of measures 0 and embedding into CPD, but I won't talk about that. That approach is slightly different. And similarly, Fedosov constructs a deformation quantization on symplectic manifolds. Again, by embedding, we induce it on a submanifold. And all quantizations depend on the embedding. And I now go to the very final slide. So how important is the role of CPN and CN for Berezin-type quantization? We can replace them by some other symplectic of Poisson manifold N, but N should have a reproducing kernel Hilbert space. That means it should be equipped with coherent states. And it should also have Berezin, Odzyevich, or Fedosov quantization. One of them should be there. Then we can talk about deformation quantization. And next, can this be generalized to other methods of deformation quantization? You know, Kontsevich quantization is there. Kontsevich's deformation quantization. That's way more difficult. These are more simple than that, but we are trying it for that also. And in physical examples, is this method useful? So, you know, quantum Hall effect, Berry's phase, these geometric quantization plays a huge role in this. So now, or in the situations when the Hilbert space is obtained from restriction of the Hilbert space of quantization of CPN or CN, and yet the parameter space is some other arbitrary manifold. In such situations, can it be useful? So, for example, I think, if I'm not mistaken, simple harmonic oscillator, the Hilbert space is just all analytic functions, or they are analytic, right? And is there any restriction on CPN has homogeneous polynomials of degree n. I think that also appears in quantum Hall effect at some point. I don't remember exactly, but CPN.
CPN. And you see this, of course, the star products talked about. But on
wait,
CPN,
sorry,
on
excuse me.
CPN.
Yeah.
No,
so-
and we see the star products.
Star product,
stuff that you
everything
talk
on this
about, because the
CPN.
magnetic field plays the
Yeah.
role, the inverse of the magnetic field plays the role
I
of
see.
the H, your H,
Oh,
the
H,
parameter H.
the parameter H cross.
Yes.
Okay. Yeah, okay. So possibly it can be reduced to some submanifold of interest. I don't know. This is a very general theory. We are still just a very new venture. So I still not thought about all the concepts. There are many questions, right? Uncertainty principle and I mean, if you have a star product whose first order is proportional to the Poisson bracket, you should be able to get a uncertainty principle. If the Poisson bracket is non-degenerate, you should be able to get an uncertainty principle of those two symbols. Things like that. There are many, many questions I'm trying. So, okay, sorry. Okay.
Are there any questions?
Thank you very much. I have a very naive question because I could see that there are similarities between your two approaches. Are they complementary or how do they meet?
I don't know, she'll be able to tell better.
Are your two approaches complementary or because you go to CPA, don't you? Yes. Yes. So it's not, you wouldn't know how to do that. Yes. Okay. Thank you.
Yeah, so I'm really not an expert of anything that you said. I was just wondering from a mathematical perspective, because that's something I've done for other reasons, embedded closed manifolds in something bigger and tried to see some intrinsic properties. But what you said is that what you obtain depends on the embedding.
Yes.
So isn't that something that you don't want?
No, that is something I want.
So why can you explain why you want it? Yeah.
Because different situations require different embeddings. So I want to apply it to some explicit examples. So I want to have it in general situations so that, you know, for example, if some physical examples do work, they will all be different embeddings, I guess. So, so that's why I would like it to have that flexibility. And okay, so I didn't show the references. So these are some references for Poisson structure. And then this is the seminal work of Berezin. And so I actually worked on the Odzievich also. So this is reproducing kernel Hilbert spaces, Berezin and Odzievich. And then I had few papers with Kohinoor Ghosh. And then there are some topological papers which I have cited here because of the cell decomposition. And this is Fedosov's seminal work. This is Odzievich's. And the one I wanted to show was, yeah, Paulsen and Raghupati, an introduction to the theory of reproducing kernel Hilbert spaces. They show how submanifolds can inherit reproducing kernel Hilbert space. So it's possible to have it. And yeah, that's it.
Any questions? I have one sort of naive question, which is that very often you hear of, you know, when you're looking at odd dimensional manifolds, and there are things called contact manifolds.
Yes,
right?
yes, yes.
So how does that framework relate to what you're doing?
So if contact manifolds can be quantized by embedding it into simplex. The contact structure is that non-integrable.
So I have very little knowledge of it.
I
know it
used to
works
remember.
for odd dimensional manifolds.
Yes, yes.
So
contact manifolds can also be quantized in some sense, but again, you need one more extra dimension.
Yeah.
But here my attitude is very different. The attitude is I embed it there and intrinsically pull it back from ambient space. So I feel that the two are a little bit different, but I'm not sure. Yeah. Yes.
To get some sense of Poisson bracket. So for odd dimensional manifolds, through this embedding.
It's a degenerate. It's a not a non-degenerate one, obviously, but you can still induce it from the. I mean, I am still calling it Poisson bracket, but and it satisfies Jacobi identity and all that, but it's not a non-degenerate Paycha bracket, as you would say. Yeah. But it is there. You can induce it from there. So just by restricting and then removing all the coordinates in this special coordinates, and then saying it's actually coordinate independent. Jacobi identity also works because you could work in Darboux coordinates over there in the ambient and try to work out the Jacobi identity. It took us a lot of time, but finally we got it. Yeah.
Any more questions?
I mean, the Paycha bracket could even be 0. Oh, if it is not 0, what is it? Yes, I don't know. Actually, Professor Parameswaran has some examples in which
Maybe.
So if you have an odd dimensional manifold that you're embedding, I'll just close it, okay. So if you embed an odd dimensional manifold and you do the pullback as you're doing, is you will get some structure. I suspect it will be closely related to, there is a structure that arises. If you have, imagine you have a manifold, odd dimensional manifold. I cannot define a Kähler structure on it, but there is a way to think of it as the cross-section of a cone in one high dimension. That is called the Sasakian structure. And that will induce a certain analog of the Poisson bracket. I suspect that's what you will find.
I see, Sasakian structure. Okay.
Yeah, it would be very nice if that's the case, but I can't say for sure at this point.
Okay. Great, thanks.
Any more questions, comments? If not, let's thank Rukmini.
Thank you.